Okay. First, a little bit of a clarification on word got back to me and makes my soul smile just a little bit. The little part of my soul still left. Someone actually told one of the TAs, Dr. Eschenberg never taught us that. And when I hear that, I go, oh, you should have called me into lab. I would have shown up. And it involves that whole idea of you've got a positive charge and a negative charge with regards to electric potential. The positive charge has positive potential, so it kind of looks up like this and then comes down, and then the negative charge takes over and then it goes down and like this. And the E fields point where you can think of it as like a gradient, where the E field basically says this is downhill. And so when you connect all the lines, you see that they kind of bow and do this weird thing. And so the electric field lines look like this. The positive field lines come outward and do this. So really what this is like if you've ever had like a topographic map, this is just showing you where the slope is. It's pointing down and it's kind of curving around like this. The, what to pick? Oh, the equipotential lines are the lines where they all have the same potential. So these are the points at which they all effectively have the same altitude. So these are the equipotential lines, equipotential. So they all have the same potential, whereas these are the E field lines. And they show slope. So to mark the equipotential lines, it's a lot like, I mean, if you had a topographic map, it would just be like this. If you're looking at it from the side. And that's if you have two charges. Now, in one of the quizzes, they were like, well, show us if you just had a single charge. Hold on, let me get this thing straightened out. Open, open, open. Wait, let me put one light on it. There we go. All right. So with a single charge, you can kind of simplify it by just thinking about if you just looked at that. I mean, if you just kind of drew that. But truth be told, in a single line or in a single charge, if you have that single positive point, it's a lot like the potential lines are looking like this. The E field lines radiate outward nicely rather than doing this bowing stuff over here. So really, it's a lot like these are the slopes for a top of the hill. Everything goes downhill in a particular direction depending on what side of the mountain you're on. And then these are the equipotential lines, the lines of the same altitude. So if we were to look at this positive charge from the side, the equipotential lines would all have the same effective height or potential. And so that's all that it is. So there isn't that much of a stretch to go from this to this. All you really have to remember is that these just basically continue on and loop around. And so those are equipotential, E-field lines, all that fun stuff. And it does show up in quizzes in a few of the TA's sections. Now what we're going to do is we're going to talk about circuits. And the first thing that we need to talk about are the symbols. We've kind of talked about capacitors. We'll go in more into detail in another like 2 weeks. It's the room of E field. Now granted, capacitors are way smaller than a room of E field, but we've done examples where you have one of the walls is positive, the other wall is negative. Everything in the room has a consistent E field. And the symbol that we draw for this is the two plates parallel, same length in the vertical. And we'll get to this later, but I just wanted you to understand that there's a symbol for this. There is also a symbol for
the capacitor?
Yeah, that's a capacitor. Yeah. There's also a symbol for a battery, which we've talked about before in potential differences. A battery looks like this. One of the lines is long, one of the lines is short. The long line is positive, the smaller line is negative. And so you get, like, typically they just write V, which is the voltage of the battery. And in a case where if you started here and you moved there, your change in potential will be positive V, whatever that battery strength is. So if this was a 10-volt battery and you compared the potential from there to there, the potential would increase 10 volts or whatever the strength of the battery is. If you went from there to there and looked at your change in potential, it's negative V. And what we're going to kind of do when we're talking about circuits is the idea or the analogy that circuits are like streams. And batteries are like water wheels. So what does a water wheel do? It takes water and lifts it up from a lower to a higher gravitational potential. So water comes in. This is the battery. And then the water comes out at a higher potential. Much like a water wheel. Water flows in, the water wheel picks it up and moves it to a higher gravitational potential. So think of batteries as like water wheels. It physically moves stuff upwards in potential. Now, in these batteries, there's going to be a symbol called a ground. The ground symbol looks like this. And the ground symbol analogy is it is like an origin in a motion problem. Like a 2D motion, 1D motion, that kind of thing. You always need this is the circuit's reference point. Now, grounds have two main qualifications. One, first is a freedom, then there is a restriction. The ground can be placed anywhere. In reality, you can put that ground anywhere on the circuit. It doesn't really matter. Note, I typically put the ground here. If you look at the battery, I typically put the ground at the negative end of the battery. That's where it usually goes. It could go anywhere, but I generally put it there. The other thing about this is that, like Highlander, there can be only one. Do we get that? You get that? All right, bad pun. I love bad puns, horrible puns. I especially like them when you take photographs of the puns in lab and then post them on Twitter. Love it. Like what happened last night. Genius. Look it up on Twitter if you want to see.
This is like an origin and a motion. Read what you read.
Batteries are like wire, circuits are like streams. Ground. Origin and excuse me. More coffee is necessary. Stat. See, she's even walking out of the room. Yeah, look at her. It's like, oh, a motion problem. Dude, I'm going to file a motion. I'm going to teach. Let it be known that Physics 14 in the spring, if I ever teach it, will no longer be at 8 a.m. Let it be so. Well, I'm not sure about that part, but I'm not doing this again. All right, so I typically put it at the ground here. There can be only one. There was a student who was like, well, what if you have 5 grounds? And I'm like, don't do. I guess technically you could, but in 214 rules, it's just going to mess everything up. So now, we've got ground, we've got batteries, we've got capacitors, which we're going to kind of set aside for the moment. And there is resistors. Now, resistors look like this. I mean, if you really find the neat ones, they look more like Charlie, the pattern in Charlie Brown's shirt. And resistors are like, let's talk about, we kind of dabbled in this at the beginning for electrostatics. You have conductors and insulators. Conductors readily allow charges to pass. Insulators inhibit charges to pass. And most of the charges that we're talking about are electrons, the negative charges. Resistors fall in between they allow charges to pass but not easily. This passing of electrons, which I'll just write E with the minus sign, is known as current. So the idea of current, we have the fundamental units. You're familiar with length, meter. You're familiar with mass, kilogram. You're familiar with time, second. And force isn't a fundamental unit. I'm going to go on my brief rant. Well, why isn't force fundamental? Well, a Newton is a kilogram meter per second squared. You cannot have a fundamental unit that is made of other fundamental units. A Newton can be described in the form of 3 other fundamental units. You can't describe length as a function of anything else. You can't describe mass as a function of anything else. You can't describe time as a function of anything other than time. And now we have to introduce the idea of, and I'll have not fundamental and let's ignore count for the moment because we really don't deal with count. And this is fundamental. And as much as the metric system says that for the most part, it is superior to the imperial system, there are quirky little things that, if they were truly consistent, I'd be more happy with it. They say that charge, which is just a coulomb, or C, that C is not fundamental. And that current, which is typically given as I, that I is current and current is fundamental. So what is current? Well, current is the measurement of the flow of charge. If, let's say for a moment that we just had a wild herd of electrons and they were flowing in one particular direction, and you had 10,000 electrons passing a point every second. What is its current? So we've got 10,000 wild electrons entering that window every second. We got 10,000 electrons flowing out every second. So 10,000 electrons are coming in and out of the room. Current is defined as the amount of charge divided by the amount of time. The amount of charge is 10,000 electrons times, and I'm really not interested in the positive or negative at any, not right now, 1.6 times 10 to the negative 19th coulomb per electron divided by second. And what we get, well, that's 10 to the fourth, so this is 1.6 times 10 to the negative 15 coulombs per second. And that is how current is, those are the units for current. Current, coulombs per second, and 1 coulomb per second is equal to 1 amp. That the amount of charge flowing by as a function of time is measured in coulombs per second, and it is measured in an amp. The thing that that bothers me is that you've just told me that an amp is a fundamental unit, which it is, and there's a reason why, but I'm going to present my rant first. But a coulomb isn't. However, what is an amp? An amp is a coulomb per second. So how can you tell me that this is a fundamental unit and inside is another fundamental unit? In fact, there's not only one fundamental unit, there are two units. There's a time unit and a charge unit. And it's simply because from an experimental point of view, you can get your little digital multimeter to read the current. It could be easily done. But what you can't do is go down to Walmart and pick up 1 coulomb of charge. I've never been down that aisle where there's a jar that says there's 1 coulomb of charge in this. You can't easily quantify charge. You can see what it does, but you just can't easily go, that's it. Just like you could say, well, that's a meter. This is 100 grams. 5 seconds have just passed. But those are easily quantifiable, just like current. And so that's why current is known as a fundamental, I would probably say quantifiable or easily measured, fundamental, easily measured, something like that. But that's the current. So in our first example of a circuit, the battery is going to have a potential difference of 10 volts. And this resistor, and let's talk about resistors for just a moment. Resistors have a resistance ability to inhibit current flow. Units of resistance are measured in ohms. So that is the unit of resistance. And the symbol that we use is the capital omega. I typically more write it like that when I'm writing quickly. So the resistance here, let's say, is 50 ohms. So it has a resistance. When you've got a circuit like this, the current labels flow from the positive lead back to the negative lead. And so this is the current I. And what I'm going to do is I'm going to put a ground on that point there. So what we're going to do is we're going to initially just study this circuit from very fundamental concepts and answer everything about it. The first thing that we'll do is identify potentials. If it is along the wire and it doesn't pass through a battery or a resistor, it's at the same level. You can think of this region right here as this flat area at the bottom of the hall. So everything on this floor down here is at the same potential. And what I've done is I've attached, if I didn't attach the ground to it, you could not tell me what potential it is. But since I've attached the ground to the potential, or the ground to that wire on the right-hand side, its potential is now what? 0. So let's assume that sometimes, all right, the garbage can is the ground symbol right here, which means that the potential at this point here is what? 0. It's obvious. So now I'm going to walk over here. What's the potential over here? 0, because it's all attached by the same wire. If there's no resistor between me and the garbage can, there's no battery between me and the garbage can, the floor is flat, effectively. The battery you can think of as the water wheel, and the battery is this pathway right here. It goes up to the higher end of the room. So if the potential difference of the battery is 10 volts and the right side is ground, the potential on the right side is 0. And the potential on the left side is what? 10 volts. Because you went from 0 across a 10 volt battery from negative to positive. So all the potential there is 10 volts. Now the red region here is a lot like the region of the room at the top. It's flat, it's all at the same potential, just like all the wire here, is that same potential. This resistor here is a lot like the path coming back down. So in our arrangement, or our way of thinking, the current comes this way, it gets to the battery lifts it up to a higher potential, it goes across the back of the room, and it comes back down through the resistor. Just as I say that the batteries are a lot like water wheels. It takes the water and it lifts it up to the higher part of the room. The resistors, the analogy that I use for them, are like waterfalls. It falls downhill. So, batteries, water wheels, resistors, waterfall. Now, we need to know about a couple last things about the current. The current has a relationship, and technically it's going to be the total change in potential divided by the resistance. The total change in potential is just the strength of the battery. So 10 volts. The resistance is 50. So I is 0.2 amps. So the current passing through the wire is 0.2 amps. And then you could measure how many electrons are flowing, because if you now know I, you could figure out from T delta Q. Now, one of the things that, the way that electronics label their parts is that the current goes away from the positive and then it comes back to the negative. And this is a relic. I haven't figured, I really need to read up why we haven't made the decision to make this change. Current flows in the opposite direction of the electrons. So in this case, the currents are flowing clockwise, but the actual electron flow is going this way. And it does make a little bit of sense, because when you look at the high potential and low potential of the battery, the electrons should flow to the highest and away from the lowest, so they should be spinning in this direction. But the current has it spinning in the opposite direction. This is mostly because this is an artifact of back when they were doing research on electrons and protons and figuring out how current flows and stuff. They were convinced that it was the positive charges that were flowing. And so they set it up so that current was the flow of the positive charge. But then they realized it was actually the electron that was moving. And then they just said, let it be known, current is in the opposite direction of the electron flow. So that's it. That's as far as the argument that I want to go to. I'm sure there's a book somewhere which makes it far more detailed.
How come the arrows in the battery were going the other way?
How come the arrows on the battery were going the other way? You mean this arrow and that arrow?
Yes.
those are the arrows of current. So let me draw it another, without the battery or anything like that. If I tell you that the current is flowing like this, that the current is flowing in a clockwise rotation, then the electron flow is flowing in a counterclockwise direction because the electron flow is opposite of the current. In reality, it's the electrons that are doing the moving. But in our analogy, we're going to say that this water, which is the opposite flow of the electrons, is what we're thinking about in this analogy. Okay, so we've studied what goes on in this very, very simple circuit. And I do have a question about this circuit that we'll need to know for future, a few future questions, as in future as in the next like 15, 20 minutes. If I told you, using our water flow analogy, and you measured the flow of water going through the battery, and it was 1 gallon per second. 1 gallon per second. How much water would be flowing through that part of the circuit? It's kind of a trick question because I'm expecting the obvious answer. 1 gallon per second. How much water is flowing through the resistor? 1 gallon per second. Likewise for all the parts. For in something like this, where it's a continuous loop, if there's 1 gallon per second flowing through the pipe in here, there's 1 gallon per second flowing through the water wheel. There's 1 gallon per second flowing along the pipe at the top of the room, and there's 1 gallon per second of flow coming down. It's a lot like the Bernoulli's equation, or no, more importantly, equation of continuity, conservation of flow. That the amount of water going into the system is the same as it's going out. Why am I making this point? Because in a couple of minutes I'm going to have a few people pick you up. So, do you have somewhere else to go? No? You're just hanging out? Just chilling? Okay. So, let's start the confusion. There are the concept of equivalent resistors. That if you had two resistors, R1 and R2, and they're placed back to back, you could yank them out of the circuit, replace them with an equivalent resistor, REQ, and the circuit would act as it was before. These, when they are running from one to the next one, these are parallel resistors. Oh, and one thing that I didn't really, I talked about this in the determination of current. This is known as Ohm's law. Sorry about that. Ohm's law is kind of a big deal. Now, how do you find the equivalent resistors for this? Well, you know how I talked about current, and there is the current flowing through the equivalent resistor, the current flowing through the first resistor and the current flowing through the second resistor. So what do you know for a fact about these three currents? They're the same. Why? It never splits. If you've got 10 gallons per second going through the first resistor, you got to have 10 gallons per second flowing through the second, and you got to have 10 gallons per second flowing through the equivalent resistor. So I1 is equal to I2, which is equal to I equivalent. Now there is another part there is, say if we're thinking again about this walkway right here, and rather than have one resistor running the entire length, we've got one resistor that starts here, that ends in the middle, and then the second resistor goes on to the top. And there is an equivalent resistor which basically runs from the top of the hill down. What can you tell me about the change in heights for the two resistors versus the one equivalent resistor? They're the what? They're the same. So if I went up two resistors, one resistor and two resistors, I'm still at the same top of the hill versus one equivalent resistor which goes up the entire length. So that change in potential, when you add delta V1 and delta V2, you will get delta V equivalent. That those potential differences must add up. I'm sorry. And the real question is, why did I use the word parallel? They're series resistors. Yes, I will definitely be moving this class if I can't even identify a series resistor. I know all of physics is now ruined because I used the wrong word. So these potentials add up to be this. What we do is we now hurl in Ohm's law. Ohm's law can be rewritten as IR is equal to delta V. So we can replace this. I1 R1 plus I2 R2 is equal to I equivalent R equivalent. And what do we know about I1, I2, and I equivalent? They're all the same, so they can cancel. So R equivalent is equal to R1 plus R2. So if you had two resistors in series, you just add them together, and then the equivalent resistance and you get 30 ohms. And so that what we've done here is the derivation of equivalent resistance for series resistors. The things that you need to know is this, obviously that, and this. Then everything else is substitution. Now we can get to parallel resistors. parallel resistors,
So for the delta V1, V2, is that absolute value or not?
well, really what I was doing here was I was doing like placement, like these spots.
But in the equation?
Generally they all have the same sign, so I'm not
So it
really,
doesn't matter.
I don't think it matters. I mean, it's either going to be delta V1 will be negative and delta V2 will be negative, or they'll both be positive. So you don't really need the absolute value sign. So R1 and R2 are in parallel, and you get R equivalent. And now we need to figure out, well, what do we know delta V2, delta V1, and delta V equivalent? What do we now know about those three? Those three potential differences. They all have to be the same. Let's say, for instance, that this side of the room wasn't the water wheel, but it was another waterfall. That there was a water wheel bringing water up and pumping it in at the top of the room. The water forks. Some of it goes down that side, some of it goes down that side. They both started at the top, they ended up at the bottom. Is there a difference in the height that was dropped dependent upon the path? No. They both started at the top of the room, they ended up at the bottom of the room. The change in the height is the same. So the potential difference for 1, for 2, and the equivalent are all equal. They're all the same. Or actually, I should write that. Now let's look at another quantity. I1, I2, and I equivalent. They're 10 gallons per second the water wheel is pumping up to the top of the room. 3 gallons per second is coming down on this side. So 10 is coming into the room, 3 is coming down the room on that side. How many gallons per second are we here? 7, exactly. And why? Because the amount of water coming in has to be the same as the water coming out. So 10 gallons per second coming up there, I equivalent must equal I1 plus I2. That those currents must add up to be the total current. So this is a big deal, and that's a big deal. And what we're going to do is we're going to use Ohm's law again. I1 delta V1 over R1. I2 delta V2 over R2. I equivalent and you get this. And we know that those are all equal, so we could divide them out. So this leaves us with 1 over R1, 1 over R2, 1 over R equivalent, or you could say R equivalent is this. So what we've done is yes, question.
Okay, at the top, isn't that very, like, the first few things you wrote, doesn't that go with the other page?
Yes.
Can you, like, make a line?
That help?
Yeah.
Okay. Yeah, so everything above is for series. Everything below is for parallel. What does that? Ooh, there are people. It doesn't mean anything. Everybody just. All right. I'm about to hear a murmur. The sky is blue. Yeah. Yeah. So. All right. So now what we're going to do for the next so many minutes. It's 8:53. I got an atomic clock up here. We're going to go. We may go full time. I don't know. It's not like you have organic class today. I should just have. I'll go over there and I'll teach in there for a while. Huh? Oh, they told me. Question?
Yeah, you could tell us, or give us like a preview of what's going to go in the first test. Like
Yes.
last semester, you told us the kinds of problems.
Yes.
that were gonna be on there.
Yes.
Could you share that today?
What's on the test?
I'm riffing on some good stuff, and you go, well, what's on the test? The bottom, well, actually, okay, fine, I'll tell you. I don't know exactly what the appetizer is going to be.
Yeah.
One of the main problems is going to be an E-field vector addition problem. Multiple charges. I don't know exactly what kind, but it's going to be a fun one. The next one is going to be working with circuits. You're going to be given an arrangement of circuits. You're going to ask to find some of the things that we're going to do in the next like 20 minutes. And this is going to, the stuff on the second page of problem set 2 is second problem material. And I will now receive your applause once I make this statement. Will Atwood's machine be on the test? No, it will not be on the test. Exactly. Thank you. Now 213, they're getting a full Atwood's machine. I'll give it to them. Question on the left. Question in an individual up against the far wall in red, kind of a light pinkish with a hat on. You had your hand up. Oh, you didn't? You just had it like this and now, oh, you're stretching. Oh, okay. Simple circuit. Five ohms, 10 ohms, 8 ohms. Battery is 20 volts. Put that there. And what I want to know is potential at A, potential at B, potential at C. These are points A, B, and C. I want to know the current flowing through the circuit, which is typically called I/O. I want to know the currents flowing through each of the resistors. So we're going to do it this way. So I want the current flowing through the battery, or I want the potentials at A, B, and C, and I want the currents flowing through the resistors 1, 2, and 3. Resistor strengths are 5 ohms, 10 ohms, and 8 ohms. Battery is 20. When doing a problem like this, the first thing that you want to do is find REQ. That's it. That's the first thing that I care about. Now, when you do this, really the only thing, this is a very simple example, is you want to simplify it by doing successive equivalent resistances. So the first thing you do is you can't simply take these three and smoosh it down to 1, but you know for a fact that these two are in parallel. So you're going to smoosh these, and you will hear that word a lot, smoosh, to an R1 and an R2-3. Now, what is R2-3? R2-3 is a parallel equivalent resistor, so 1 over R2 plus 1 over R3 inverted. So this is 1 over 10 plus 1 over 8 inverted. Now, for something like this, numerically, and don't use this, the 4.44 repeat, what you should do when you're working with circuit problems in the middle of the circuit, I've got a TI-84 Plus. I don't know how to do it on many of the other calculators. I hit math, return, and that gives me a fraction. 40/9. 40/9 is the equivalent resistance of 2 and 3, and that number is exact. Now, why am I using fractions in the middle? Because I know that you guys are a bunch of plug-and chugging fiends who love just ripping bits of information off. If you went 4.44 and that was it, you'd be chopping off information and you would be introducing bit rot into your circuit. If the circuit doesn't have like 3 resistors, it has more like 10 resistors, that successive repetition of rounding will disrupt your final answers. It will add up and it will make it look confusing. So I have a 5 ohm resistor and a 49th ohm resistor. They are in series, so I smoosh it down. I get REQ, and REQ is 5 plus 40/9.
So is REQ just like combining all the R's on
Yes.
hypothetically?
It's the equivalent of if I took those 3 resistors out of the circuit and I replaced it with REQ, it's the same thing. Now REQ is 85/9. In the idea of when I'm asking for, give me the equivalent resistance of the circuit, the answer that you give me will be in numbers like this, 9.44 ohms, and leave it like that. But in terms of continuing to use values, use the 85/9 for the next step. Yes, question?
So why is it R23? Like what happens to R1 right there for R2?
Well, R2 and R3 got smooshed into R2-3. R1 just came down normally. This is R1, that's R2-3. You really do have a drinking problem. You cannot handle your liquids. All right, now. So nothing happened with R1 other than it was passed down. The worst one, there was someone like row 10 that dropped something like that and it was half full. So it did this slow grinding thing down 10 rows and it literally just hit the garbage can and it was just like, it was awesome. Stage 2. Find I naught. Find the current running through the entire circuit. This is the current that's flowing through the resistor. So I naught is that delta V, the battery strength, divided by Req. Delta V is 20. Req is 85 ninths. We get 2.12 amps or 36/17 amps. And I will continue to use the 36/17 amps. Now let's knock out some easy potentials. What's the potential of, let's do the easy one. What's the potential at C? It's 0. It's attached to the ground. What's the potential at A? 20. It's at the top of the battery. Now, there's another easy trivial current that we could just go, it's that. It's the current running across I1, or it's the current I1 running across resistor 1. I naught is 2.12 amps. So what's the current I1? 2.12 amps. Did the circuit fork? No. So I1 is equal to I naught, which is equal to 2.12 amps. Now this is a lot like, this particular problem is a lot like a Sudoku puzzle. You just can't answer questions that you don't have all the information to. The true current equation that I'm looking for, V high, V low over resistor. If you have 3 of those 4 quantities, you can identify the value. For VB, VB in this case is V low when compared to VA. So I know V high, that's 20 volts. I know the resistor from there to there, that's R1. I know that. And I know I1, the current flowing across the R1 resistor. So I can now identify the resistance at B. So IR V high, huh?
How do you determine what's V high and V low?
V high, V high is whatever is the furthest upstream.
Okay.
And I tend to use it as, this is how I'm really using magnitudes all the time. So this is higher than that, that is higher than that. It's because it's going further downstream. The further downstream you go, the lower you are. If you start, like, if you go river rafting, the point at the beginning of the stream is definitely higher in altitude than the end of the stream. So, to get the current going across that resistor, if you took the high potential and subtracted it from the lowest potential, and you divided it by R, you've got the current. You just know. It's, I mean, this is a variant of Ohm's law. V high is 20. I is 3617. R is 5. And this is a multiplication. So I get a voltage value of 9.412 amps, or no, not amps, volts. And then 1/60/17 volt. Yeah, as a fraction. So we now know what VB is. What are we doing?
No.
We're finding everything about this circuit. I want to know every single potential drop across every single resistor. I want to know the currents flowing through every single resistor. I want to know the R equivalent. I want to know the total current. I want to know everything.
So we need to have decimals and fractions at every point.
I would say when I go, if I don't ask for it, don't write it down as a decimal. Keep it as fractions.
But we're looking for the points. So
Yeah, but we're looking at the various points. So when I want a number, VB, don't give it to me as 1/60/17. Write it out as 9.412. But when you're continuing your problem, keep it in fractions. Someone had a question. Yes. First and then second. Purple.
Where did you get the 20, like, for the,
Where did I get the 20?
yeah,
For this?
no, for V low, like, I mean V high.
V high is VA. V high is the potential at that point. V low is the potential at that point. V high is the same potential as that length of wire, or 20 volts. V low is the same potential as VB. In the back, over here. Someone had. Oh, not light blue, darker blue, 2 rows back. You had a question. You, yes.
How do you know that I
I naught is equal to I1 in this case. Why? They never force. Question. Is VC even lower than VB? No, yes. I had to think about what you're actually saying. VC is attached to ground. VC is 0. VB is 1/60/17, or 9.412. So VB is greater than VC. All right, one last thing that we got to cover before I think we're done. 5 minutes.
So does this stream start at the ground or the battery? Does that make
Does the
sense?
stream start at the ground or the battery? It could start really at either. I would think that the ground is at the base right underneath the water wheel, and it lifts it up. The last bit, I2 and I3. Now I've kind of pulled them apart. I2 is this bit. I3 covers that bit. What do I know about the high ends of R2 and R3? They're both at VB, which means both of those values are 1/60/17. V low of R2 is the same as V low of R3. They're both attached to the bottom, which is attached to ground. So V low is both 0. R2 is 10. R3 is 8. All right, now I'm going to have to, I got 3 minutes, so I'm going to speed it up. The I2, V high minus V low over resistance, 1/60/17 divided by 10. Here it is 160 divided by 17 over 8. I get 0.94118 amps. And I get 1.17647 amps for this numerically. And what happens when you add the two together? They add up to 2.12, which proves the notion that the currents do add up together. All right, what we're going to do is, obviously, there's going to be a lot more work with circuits on the Friday tutorial, which will be here from 2:30 to 4. So I will see you then.